Welcome to This Explainer. Today we are diving into how your kidneys act as the absolute master controllers of your body fluids and your blood pressure. We're going on a pretty fascinating journey here, going from perfect, flawless physiological function all the way to catastrophic system failure. Look, every single time you eat a really salty meal or chug a gallon of water, there is a microscopic war being waged to keep your body perfectly balanced. If you've ever wanted to understand exactly how the human body handles a massive influx of salt, or why a failing heart literally drowns the lungs in fluid, well, you are absolutely in the right place. Okay, so here's our roadmap for This Explainer. We've structured this to lock all 10 of these interconnected, complex physiological topics into your mind permanently. We're covering 1. Renal pressure and fluid feedback, 2. Hormonal and nervous fine-tuning, 3. Adapting to salt intake, 4. Heart failure and fluid overload, and finally, 5. Edema, cirrhosis, and capacity. Let's get right into it.
Section 1. Renal pressure and fluid feedback. So, we have to start with the absolute foundational rules of your body's plumbing system, specifically pressure natriuresis and pressure diuresis. These are the powerful, intrinsic mechanisms your kidneys use to regulate sodium and water. And the crazy part? They do this completely independently of any outside signals. Notice the stark difference between the acute and chronic responses. If your arterial pressure acutely spikes by just 30 to 50 millimeters of mercury, say you're super stressed or doing a heavy workout, your kidneys intrinsically crank up sodium excretion by 2 to 3 times. They do this entirely on their own. Literally, even in an isolated kidney with no nerves attached, this happens. But then, look at the chronic response. Over time, chronic high blood pressure actually suppresses the renin-angiotensin-aldosterone system, or RAAS for short. This heavily amplifies the amount of sodium and water you excrete. It's just an incredibly elegant, built-in defense mechanism.
Now let's follow the actual sequence of events when you drink a bunch of water. It builds into this elegant little cascade that naturally forces your body to excrete the excess. So step 1, you drink more fluid than you're losing, and it temporarily accumulates. Step 2, this extra fluid raises your overall blood volume and your mean circulatory filling pressure. Step 3, that extra pressure pushes more blood back to your heart, which we call increasing your venous return. Now for step 4. According to the Frank-Starling mechanism, a higher venous return is kind of like stretching a rubber band. The more blood that flows back into the heart, the harder the heart pumps it back out. So your cardiac output goes up, and consequently, your arterial pressure goes up. Finally, step 5. That slight elevation in arterial pressure acts directly on your kidneys, triggering massive pressure diuresis and natriuresis to just flush all that excess right back out.
Think of this whole process like a perfectly balanced seesaw. This super efficient feedback loop keeps our actual blood volume and extracellular fluid practically identical day to day. It makes our normal, everyday dietary changes completely imperceptible to our overall fluid balance. And because that pressure natriuresis curve is incredibly steep, your blood pressure only has to change a tiny, barely noticeable amount to trigger a massive response from the kidneys.
Section 2. Hormonal and nervous fine-tuning. Okay, now we're shifting focus from that basic pressure plumbing to the body's smart valves. While pressure natively drives excretion, we also have nervous and hormonal systems that fine-tune things without needing major blood pressure changes. Enter angiotensin II. You can think of angiotensin II as your body's master hoarder. If you're on a low-salt diet, angiotensin II levels shoot up to tightly conserve whatever sodium you have. But if you eat a high-salt diet, it's supposed to suppress itself. The problem? In some people, whether due to genetics or slight kidney damage, it actually fails to suppress. When that happens, your kidneys stubbornly refuse to let go of the sodium. So what does the body do? It forces your blood pressure to skyrocket just to trigger that basic pressure natriuresis we talked about earlier. And boom, that is exactly what causes salt-sensitive hypertension. This matrix right here is a fantastic, high-yield memory aid you absolutely want to lock down. It shows how beautifully specialized these different systems are. The sympathetic nerves, they respond to pure emergencies, like a hemorrhage, by restricting blood flow and conserving volume to literally keep you alive. The RAS and angiotensin II system handles low sodium intake. Then you have antidiuretic hormone, or ADH, which is your main defense against water deprivation. It specifically concentrates your urine to save pure water. And finally, atrial natriuretic peptide, or ANP. This is essentially the body's emergency relief valve. It triggers immediate sodium excretion the second your heart atria physically stretch from too much fluid volume.
Part 3. Adapting to salt intake.
Let's really look at what happens when you drastically increase your salt intake. We're talking sometimes up to 10 times your normal amount. How does the body handle that? Well, this timeline brilliantly illustrates the multi-system defense. Within the very first hour, that extra fluid expands your extracellular volume, which stretches low-pressure receptors in your heart. By hour 12, this stretch reflex actually decreases your renal sympathetic nerve activity, which finally allows you to start losing that salt. Hit 24 hours, and the ROS system, including angiotensin II and aldosterone, is completely suppressed. Over the next few days, a slight rise in arterial pressure triggers pressure natriuresis to finish the job. But here is the massive catch. If this high salt-to-salt continues for months or years, the kidneys take physical damage, and that traps you in a state of permanent, chronic hypertension just to survive and excrete a normal, everyday amount of sodium.
Section 4. Heart failure and fluid overload. Now we're crossing the line into pathophysiology, where these perfectly designed compensatory mechanisms suddenly become a deadly trap. We're talking about diseases of the heart and circulation. So ask yourself, why on earth does the body actively hold on to massive amounts of fluid when the heart starts failing? It seems totally backwards, right? Your heart is struggling, your legs are swelling, your lungs are filling with fluid. Why keep more? The answer is a really tragic biological misunderstanding. The kidneys are completely blind to your heart's actual pumping strength. They only measure pressure. So when your heart pumps poorly, the kidneys literally think you are bleeding to death.
Let's follow this step by step to see how this fatal feedback loop actually plays out. Step 1. A weak heart lowers your cardiac output, which drops your arterial blood pressure. Step 2. The kidneys sense this low pressure, they panic, and they fire up the RAS and sympathetic nerves. Step 3. They relentlessly retain sodium and water. Now, actually, if the heart failure is mild, Step 4 kicks in. This extra blood volume improves venous return, and it genuinely helps the weakened heart pump enough blood. It's a life-saving move. But in severe failure, the heart simply cannot respond to the extra volume. The blood pressure never restores, so the kidneys never stop retaining fluid, and ultimately, they drown the lungs in pulmonary edema.
200%. Just let that number sink in for a second. The extracellular fluid volume can increase by 200% or more in advanced heart failure. Imagine carrying around double your normal water weight. This is exactly what leads to that massive, visible tissue edema. The kidneys just endlessly pack the body with fluid, trying in vain to raise the blood pressure of a dying pump.
Section 5. Edema, cirrhosis, and capacity. To wrap things up, we're going to look at how increased vascular capacity and extreme protein loss trick the kidneys into infinite fluid retention. Sometimes the heart works flawlessly, but the blood vessels or the plasma proteins are what fail us. Think of your vascular system like a closed plumbing tank. If the blood vessels physically dilate and expand, meaning your vascular capacity gets bigger, the pressure inside that tank drops. Now, even though you haven't lost a single drop of actual blood, the kidneys sense that drop in mean circulatory filling pressure, and, again, they panic. They start blindly retaining fluid just to fill up the new, larger space.
A really perfect, healthy biological example of this is pregnancy. As the uterus, placenta, and maternal organs grow, the body's vascular capacity naturally expands. The tank gets bigger. So, to compensate, the kidneys fill it up, causing a totally normal, healthy 15 to 25% increase in total blood volume.
But things take a very dark turn in a condition like nephrotic syndrome. In this disease, the glomerular capillaries become way too permeable, and a devastating 30 to 50 grams of plasma protein are lost in the urine every single day. This completely destroys the blood's oncotic pulling power. You can think of these proteins like microscopic sponges that hold water inside your blood vessels. Without those sponges, the fluid just leaks right out of the capillaries and directly into the tissues, which lowers your plasma volume. The kidneys sense the low volume, retain more salt and water, which then just immediately leaks out again into the tissues. It creates massive, generalized edema.
And that brings us to liver cirrhosis, which is honestly an absolute double whammy. First, the destroyed liver cells stop producing albumin. That crashes your oncotic pressure, so fluid leaks into tissues. Second, the liver fibrosis acts like a concrete roadblock in your veins, creating severe portal hypertension. This massive hydrostatic pressure forces fluid directly out into the peritoneal cavity, a condition known as ascites. Again, the kidneys sense a low effective circulating volume and retain more salt, which just physically worsens the ascites. It is a vicious, completely unbreakable cycle.
This summary table perfectly ties together the primary conditions we've just explored. Look closely at the pattern here because it's fascinating. Whether it's a weak pump in heart failure, an enlarged tank from increased capacity, a massive protein loss in nephrotic syndrome, or the double hit of liver damage in cirrhosis, the kidneys literally only have one single lever to pull. They retain sodium and water. This is the ultimate synthesis of how your body's master controller responds to systemic failure.
And that leaves us with a pretty provocative paradox to ponder. Why does the very renal feedback loop that was flawlessly engineered over millions of years to preserve your life during dehydration or a severe hemorrhage become the exact instrument of your demise when your cardiovascular system breaks down? It's an unyielding biological program that simply doesn't know how to stop. Thank you so much for joining me in this explainer. I really hope this completely changes how you view the master controllers of your body. Keep questioning, keep learning, and I'll see you next time.